Hello everyone, this is a lecture on DC analysis and AC analysis of differential amplifier. Differential amplifier is a very important circuit as this is the first two stages of operational amplifier. So we need to understand its working. So basically in in differential amplifier we have two transistor circuits Q1 and Q2, and we have basically a symmetrical circuit on both the sides. If we take this as an axis, then we will find it as a symmetrical circuit, and we have to apply two voltages, and we have to get output from these two collector terminals of Q1 and Q2. So in this regard, we can have four different types of differential amplifier, and to understand that, we need to understand what is a balanced output. Balanced output means that if you are taking output between these two terminals, not between this and ground and not between this and ground, so that is known as balanced output. And if you are taking output between this and ground, then and this is not used, then this will be known as unbalanced output. So we can differentiate differential amplifier in four different categories, like dual input balanced output, single input balanced output, dual input unbalanced output, like this. So in DC analysis, we have to find ICC and VCQ. That means we have to find the operating points of the circuit. So if this is a differential amplifier in which we have applied V1 and V2 voltages, and we have applied VCC, then to get a DC analysis, we have to sort the input supplies, that is small signal sources. So to get the DC analysis of the circuit, as we can see here that these two circuits are basically symmetrical circuits. So we can find the DC analysis for one circuit, and the DC analysis for second circuit can be easily drawn from that. So this is the half circuit of that differential amplifier, in which ICK and VCQ can be used for the second transistor Q2 also. So we have to apply KVL at the base of emitter loop of the transistor Q1. So we can find here that if we are applying a KVL here, then this is IB. So this will become RS times IB plus VBE plus twice IE equals to minus VE. But we can say that IB is IE upon beta DC, as IC and I can be equated. So we can find IE as, from this equation, VE minus VBE upon twice RE plus RS upon beta DC. Now, as we know that VBE is almost 0.6 volt for silicon and 0.2 volt for germanium. So generally RS is very small, because RS is the source resistance. So RS upon beta DC will become very small as compared to twice RE. So we can approximate this equation as IE equals to IC equals to VE minus VB upon twice RE. So this is the first operating point, that is ICC of the this differential amplifier. Now we have to find the second operating point, that is VCQ. So for that we can get the voltage VC here. What is the VC voltage here? That it is the VCC minus ICRC drop. And also we can find that VC voltage, VC means the voltage drop between collector and emitter, is that the VC, that is the collector voltage, minus VE, that is the emitter voltage. So we can put the value of VC from this equation. So then we can get VCC equals to VCC minus ICRC plus VE. Now what is V? VE can be approximated as VBE, because the RS resistance is very small, so we can neglect this voltage drop. So what we can get is that this voltage VE is approximated as VBE, but in the negative polarity, because this is positive sign and this is negative sign. So if you are getting the voltage VE, so we can get VE equals to minus VE. So that way we can get minus VE equals to plus VB. Therefore VCE can be written as VCC plus VBE minus ICRC. So this is the second operating point of this differential amplifier, and this DC analysis is applicable for all types of differential amplifier. Now we have to take an example to understand it more clearly. So this is the following specification are given for the dual input balanced output differential amplifier as shown in the figure. So these parameters are given, that is RC is given, RB is given, Rin or Rin2 both are given. Then VCC and VE are given, and beta DC and VB is provided. So we have to determine the operating points, that is ICQ and VCE of the two transistors. So just put the values provided in the question, and we can get ICQ and VCEQ from this equation. Now AC analysis. Now, to get the AC analysis of the transistor, the first thing we have to do is that we have to ground the DC supplies, and for calculating the AC analysis, we have to take the R parameter equivalent circuit of the transistor. In R parameter equivalent circuit of the transistor, we have to replace the transistor with this circuit. That means wherever there is a transistor circuit, we have to replace that transistor circuit with this circuit. We have to use a current source, that is beta AC IB, or we can say this is IC current, and this is the equivalent resistors at emitter. So it is R dash E. So we have got the circuit of the R parameter equivalent circuit of differential amplifier, where VCC is grounded and transistors are replaced with their R parameter equivalent circuit. Now we have to apply a KVL in these two loops, first and second loop. In this loop we can get that what is V1 is this drop plus this drop plus this drop. So V1 is basically RS1 times IB1 plus IE1 current is flowing here, so IE1 into RE dash plus this drop. This drop is IE1 plus IE2. These two currents are flowing this resistance. So IE1 plus IE2 times RE. Similarly, we can get the KVL equation in this loop also. So we can get V2 equals to RS2 IB2 plus IE2 R dash E plus I1 plus I2 Rin. Now, as we know that IB1 is IC1 upon beta, and IC1 is can be equated as IE1. So this is can be this can be written as IB1 equals to IE1 upon beta. Similarly, IB2 can be written as IE2 upon beta. And now we have to put these values in these two equations. So we can get V1 equals to RS1 IE1 upon beta plus IE1 R dash E plus I1 plus I2 RE. Similarly, we have to replace IB2 with this value. So we can get this equation. Now, as RS1 and RS2 are the source resistances and these values are very small, so RS1 upon beta and RS2 upon beta, these values can be very small as compared to RE dash times I2 and RE times I1 plus I2. So we can remove these values as these are very small. So after removing these values, we can get V1 equals to I1 times RE dash plus RE and I2 times RE. Like we can get these equations from these equations also. As we can say that RE dash is very small, that is 26 millivolt per I milliampere. So milli cancelled, and if we have I as 20 milliamperes also, then we can get RE dash equals to almost 1. So solving these two equations, we can get I1 and I2. We have to solve these two equations to get I1 and I2. So we can get I1 equals to this and I2 equals to this value. Now we have to get the output voltage V0. So what is V0 voltage? V0 voltage is this drop minus this drop. So VC2 minus VC1. So what is VC2? VC2 is minus RC times IC2. We can see here. What is VC2? VC2 is minus RC times IC2. And what is VC1 is minus RC times IC1. So this is and after solving this, we can get RC times IC1 minus IC2. And IC1 and IC2s are basically equivalent to I1 and I2. So we can have V0 equals to RC times I1 minus I2. Now we already have I1 and I2 values calculated here. So we just have to put these values into this equation. So substituting I1 and I2 in the expression, we can get V0 equals to this. And after just solving this, as the denominator is same, so we just have to calculate the numerator part. So we can get Re dash plus twice Re V1 minus V2. As Re dash plus twice Re is common in numerator and denominator both, so we can cancel this. So we will get V0 equals to Rc times Re dash V1 minus V2. Now V1 minus V2 is just the differential input voltage. So we can get the differential gain as V0 upon Vd, that is Rc upon Re dash. So I hope that these two DC analysis and AC analysis of the differential amplifier is clear to all of you. Thank you.